far beyond the reach of Earth's atmosphere, past the satellites we use every day and past the orbits where astronauts fly. There exists a quiet region of space where gravity doesn't behave the way we expect. It is a place where the pull of Earth and the pull of Sun merge into a delicate choreography, a place where spacecraft don't fall toward planets and they don't drift away into the void. They hover, they balance, they orbit the empty space. Welcome to the Lagrange Points. These 5 invisible locations are not physical objects. They have no light, no mass, no structure, and yet they are some of the most strategically important real estates in the entire solar system. Before we send humanity deeper into space, before we build lunar bases or Mars stations, before we launch the next generation of telescopes searching for life, we first need to understand these extraordinary gravitational gateways, because mastering Lagrange points is the key to mastering deep space. Our story begins with Joseph Louis Lagrange, a mathematician living centuries before the first rocket ever launched. While studying the three-body problem, the motion of 3 objects interacting only through gravity, he discovered something surprisingly. Certain positions between 2 large bodies allow a smaller third object to remain in perfect balance. He found 5 such points: L1, L2, L3, L4, and L5. These points became known as Lagrangian points, and they are the infrastructure of today's space exploration. But here's the twist: they are not stable parking spots. They are almost stable, fragile balance points where a spacecraft must continuously fight against drifting into chaos. What nature gives, engineers must maintain. Parking a spacecraft at a Lagrange point is nothing like parking a car. There is no surface, no ground, no stop command. Instead, engineers design large looping passes called halo orbits, Lagrange orbits, quasi-periodic orbits. They are not orbits around Earth, not orbits around the Sun. They are orbits around a mathematical points. A spacecraft is one of these orbits, is like a tightrope walker balancing on a moving wire, constantly adjusting, constantly correcting, and constantly interacting with the forces around them. Engineered tools used are included such as reaction wheels, thruster station keeping, fuel budget for multi-year missions, dynamical system modeling, high-precision orbit determination, and thermal and power management at extreme distances. For example, the James Webb Space Telescope performs correction every 21 days just to remain in its halo orbit around L2. If these burns are skipped, James Webb Telescope would drift away and its mission would end. But why these points matter? L1, the solar sentinel, positioned between Earth and the Sun. L1 allows missions like SOHO and Discover to watch solar storms in real time. If a massive coronal ejection is coming toward Earth, L1 is our first warning system. L2, the astronomer's paradise. On the opposite side of Earth, L2 creates a cold, shadowed, and gravitational quiet environment. This is where James Webb sees the first galaxies in the universe. Soon, NASA's Habitable Worlds Observatory will join it there. L3, the dark mirror, located behind the Sun. L3 is almost impossible to use for communication, but in science fiction, it's the perfect hiding place for hypothetical aliens or mirror Earth theories. L4 and L5, the Trojan gateways, these are the only stable Lagrange points. Gravity naturally collects dust, asteroids, and possibly future space habitats there. These locations may become engineering hubs for deep space infrastructure one day. But what are the engineering challenges of Lagrange missions? Operating at a Lagrange point requires solving problems that don't exist anywhere else. For example, radiation exposure. Nothing protects a spacecraft but its own shielding. Second, extreme temperatures. At L2, James Webb Telescope uses a 5-layer sun shield the size of a tennis court just to stay cool enough to observe infrared lights. Third, communication delay. Millions of kilometers mean signal delays and reduced bandwidth. 4. Fuel economy. Fuel must last for years, even decades. Engineers plan station-keeping burns with extraordinary precision, sometimes down to centimeter per second. And 5th, three-body chaos. Small deviations grow exponentially. The spacecraft must fight instability continuously. Lagrange points exist because gravity is not simple. The three-body problem has no general solution. Instead, engineers use numerical simulations, chaotic maps, and high-order integrators to calculate trajectories. A spacecraft at a Lagrange point is always on the edge of chaos, where orbital mechanics becomes art and engineering become choreography. This is the secret truth. We don't control the spacecraft at Lagrange points. We only guide them. Humanity is just beginning to use these gravitational highways. In the near future, Lagrange points will host lunar communication relays, deep space telescopes, fuel deposit for Mars missions, planetary defense systems, and gravitational wave observatories. These are stepping stones in the solar system architecture, nodes in a future interplanetary network. So the next time you hear about a spacecraft orbiting the Sun, the Earth, or the Moon, remember that some missions orbit nothing more than mathematics itself. They float in a harmony with gravity. They balance between worlds. They operate in silence far from home, where engineers fight the universe's most complex forces to keep them alive. Lagrange points are not simply scientific curiosities. They are the cosmic harbors of human technology, the outposts that will one day guide humanity deeper into space than ever before. This is the hidden engineering of Lagrange point, and this is how we park a spacecraft where nothing should stay still. Don't miss out. New videos drop every Sunday evening. Hit subscribe and ring the bell so you are the first to watch.